He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
Kia ora and welcome to Elemental from RNZ, a celebration of the International Year of the Periodic Table. I'm Allan Blackman from the Auckland University of Technology.
And I'm Alison Ballance. This is episode 56. And while many of the chemical elements we're covering are vital to life, I do happen to think that this is a particularly vital one. There are about 25 elements that are very important to life. 4 of them make up about 96% of the human body. We've already covered carbon, nitrogen and hydrogen, which leaves oxygen. Deep breath, everyone.
Good old oxygen. So, its vital statistics, chemical symbol O, atomic number 8. And when we talk about oxygen on the periodic table, we see the symbol O, but when we're breathing it in, we're actually inhaling O2, or dioxygen, oxygen molecules. And those molecules make up around about 20% of the air that we breathe. It's the second most common element in air after nitrogen, of course, which we've already covered. At room temperature and atmospheric pressure, 2 oxygen atoms always bond together to make the colourless, odourless gas that keeps us alive.
And when you get 3, O3, that's ozone, right?
Yes, indeed, that's ozone, or as the International Union of Pure and Applied Chemists call it, trioxygen.
I've never heard it called trioxygen.
and neither had I until we did this. So that apparently is its name that you are meant to call it, its systematic name. What do we know about oxygen? We know a heck of a lot about oxygen, actually, so we're going to have to whiz through this because there's an awful lot to talk about today. First up, what we've talked about thus far is an example of allotropy. So oxygen, dioxygen O2, and trioxygen O3, or ozone, are allotropes. Allotropes are chemical elements that exist in 2 or more different forms in the same physical state. And so we've already talked about allotropes way back when we talked about carbon. So different structural modifications of an element. So, for example, with carbon, we had diamond, we had graphene, we had graphite, we had all of the fullerenes. So they're all just made up of carbon atoms, but all arranged in different ways. So in this case, when we're talking about oxygen and allotropes of oxygen, our allotropes have got different chemical behaviours. So ozone, which is the chemical formula O3, a much stronger oxidizing agent than dioxygen O2.
Whoa, pull up. We've dived right into the chemistry before I have a chance to ask about its name, which I do like to do. So oxygen, please.
Okay, oxygen comes from the Greek words, in this case, oxygenes, which means acid forming.
Acid forming, is it really?
Yes, but to get there, we have to go through a bit of a convoluted history. So, are we all sitting comfortably? Okay.
Yeah, very comfortable. Thank you, Professor.
So, as we talked about with nitrogen, we go way back to the 1600s and 1700s, and people were busy experimenting with air at that time, and they had showed that a candle that burned in a limited amount of air would eventually go out, and at that point it would have consumed about 20% of the volume of the air. And so obviously there is something important in air. They all came to that same conclusion. So who actually discovered oxygen? Well, the jury's kind of still out on that. There's a bit of controversy here. So what is known is that some people had in fact made oxygen in the 17th century, but the trouble is that they didn't recognise it as being a new element. And so the credit these days is usually given to Joseph Priestley, and he definitely prepared it in 1774. The way he did this was by focusing sunlight on a sample of mercury oxide, HGO, and he would then collect the gas that came off. And the really important point about this is that he published the results of his experiments on forming oxygen, and he did that in 1775, which was a real shame for a guy by the name of Carl Scheele. So in 1773, which was a year earlier than Priestley, he had actually made oxygen. He called it fire air, and he did this by heating things like potassium nitrate, silver carbonate, mercuric oxide, But the trouble was that he was slow off the mark and he didn't publish his results until 1777.
That old publish or perish thing.
No, that's the thing. There's no silver medals in science, no prizes for coming second. You have to be first into print. So how did Priestley become interested in gases? Well, nice story there. He lived next door to a brewery, and what he found was that there was a gas that floated over the piles of fermenting grain at said brewery. And so he studied this gas, and he showed that it was heavier than air, and that when it was dissolved in water, it made it fizzy. So he was the first person to make a fizzy drink, because the gas that was over the fermenting piles of grain was carbon dioxide. And once he'd sorted that out, he became interested in other gases, and that's how he came to make oxygen. So with some of his experiments, he showed that a mouse lived at least twice as long in the new gas than in the equivalent volume of air. And being a brave soul, he also breathed some of his newly made oxygen himself. And he wrote that, quote, "The feeling of it in my lungs was not sensibly different from that of common air, but I fancied that my breast felt particularly light and easy for some time afterwards." And so Priestley didn't call it oxygen. That was left to somebody else who's coming up. He actually called it dephlogisticated air. And the reason he called it that was because of a thing called phlogiston, which I am not going to talk about here. If you're interested, look it up on the web. But again, unfortunately, Priestley didn't recognise it as being a chemical element. And the person who actually named oxygen was the Frenchman Lavoisier, and he actually also claimed credit for making oxygen. And the reason that it's got its name from the Greek oxygenes was because Lavoisier thought that it was a component of all acids, and hence the name acid forming. And we now know that that's actually not true. So, long story made long.
Well, thank you for that elucidation. What I take home from that is I think we should go back to calling oxygen dephlogisticated air. That's brilliant. And all these people, they kept discovering it, but they either didn't recognise what they'd got or thought it was something else.
Yep.
I think that's probably not too surprising considering you have a colourless, odourless, i.e. invisible gas.
Mm-hmm.
Now, moving on from the history, I remember from quite a few previous episodes that oxygen likes to make friends with lots of other elements. Off the top of my head, CO2, carbon dioxide, H2O, dihydrogen oxide, also better known as water.
And also known by IUPAC as oxidane.
Really?
That's its real name. That's what you are meant to call it.
Oh, okay. I'll just have a glass of oxidane, thanks.
There you go.
Okay. Anyway, there's squillions more things that have got
There are.
oxygen lumped together in a friendly fashion with other things.
Indeed. And yes, we certainly could go on with this for a very, very long time because oxygen does, in fact, react with most of the elements on the periodic table.
Why is it so reactive?
Very good question. I will give a very short answer to that, and the fact that it contains unpaired electrons. So generally things that have got unpaired electrons are quite reactive. I won't go into great detail on that because I'm sure I'll get emails. Anyway, the process that we call respiration is what chemists would call combustion. Okay, it's the same chemical reaction essentially, and that is the reaction of organic molecules with oxygen to give both carbon dioxide and water plus, and this is the important bit, lots and lots of energy. And so Earth has way more oxygen than other planets thanks to a thing called the oxygen cycle. And indeed, it hasn't always been this way. So the Earth formed around about 4.5 billion years ago, and it wasn't until the evolution of cyanobacteria, which formed oxygen from photosynthesis, that we began to get a build-up of the amount of oxygen on the planet. And this was around about 3 to 2 billion years ago and has the very good name, the Great Oxygenation Event. So prior to this, there were a whole bunch of anaerobic organisms.
I bet they were pissed off.
I bet they were. They'd been doing really, really well, and then bloody oxygen comes along and all of these things go extinct. So that's kind of sucked for them. And so the result of this event was basically the oxygen cycle as we know it today. So what happens? We get photosynthesis releasing oxygen into the atmosphere, and then we get respiration and decay and combustion removing it from the atmosphere. And at the moment, we've got an equilibrium where the production and the consumption of oxygen occur at the same rate.
Well, a big shout out to those cyanobacteria, or blue-green algae as lots of people call them, which really kicked that process off and gave us the air that we breathe today. And no, I'm not about to break into song again. Is oxygen, however, common only in air?
In fact, it's common everywhere. So obviously we find it in the ocean thanks to water, we find it in the atmosphere thanks to oxygen, and indeed oxygen is the most abundant element in the Earth's crust. And there we find it combined with silicon in quartz, with aluminium in alumina, with titanium in rutile, and with iron in hematite. And going back to the atmosphere, we talked about ozone earlier. Ozone is very, very important in the atmosphere, as I'm sure everybody knows, because it absorbs harmful UV radiation from the sun. But the astonishing thing is the actual amount of ozone in the atmosphere. If we took all of this, or if we brought all of this ozone together at 0 degrees and at atmospheric pressure, it would form a layer right around the Earth that was only, get this, 3 millimeters thick.
The word that comes to mind is fragility of that. For this incredibly important shield, that's a delicate amount of ozone.
Oh, it is indeed. And as everybody knows, there are holes in the ozone layer, and in the area of those holes, what is found is around about 2/3 less ozone. So in those areas there, you're talking about a 1 millimeter thick layer of ozone. Quite amazing. So it's very, very important in the upper atmosphere there. It is important at sea level as well. We often use ozone in water purification as an alternative to chlorine. It's a very, very strong oxidizing agent, and it just gives off oxygen when it breaks down.
That's the closest we've got so far to an industrial use for it, and we often have long lists of industrial uses for elements. Is oxygen the same?
Yes, indeed it is. And in fact, very interestingly, most industrially produced oxygen, in other words, that's oxygen that we extract from the air, is used in steel making. And how this works is that you bubble oxygen through your furnace, which contains basically molten iron and a whole lot of other stuff there. It reacts with the carbon that is left over from carbon reducing essentially the iron oxides. It turns that into carbon monoxide and carbon dioxide, which just in fact bubble off. So very, very, very important there. And also in things like rocket launches, for example, where liquid oxygen reacts with fuels like kerosene or hydrogen and gives out an awful, awful lot of energy. As an example of this, I once saw a demonstration where a visiting scientist dipped a cigar into liquid oxygen. He then lit the cigar and managed to push it through around about a 1 millimeter thick piece of steel. You're talking really, really hot. Remember, oxygen supports combustion.
Indeed, I think that's why people who are on oxygen and have oxygen tanks next to them when they have limited respiratory capacity are warned to not smoke.
Yes, indeed. Amen. Yes.
Now, a curious fact, please.
Okay, so we normally think of things that get attracted to magnets as being solids and generally being metals. And weirdly, elemental oxygen, dioxygen, O2, is in fact attracted to a magnet. It is what we call paramagnetic, and what that means is that it contains, in this case, 2 unpaired electrons. And in fact, you can do a really nice demonstration with liquid oxygen again. You pour it between the poles of a powerful magnet, and it will actually stick in between the poles, and you get a little bridge of liquid oxygen, and it supports its own weight. That's a really, really nice demonstration.
That's super cool.
Sorry. No. What do we call compounds that contain unpaired electrons? We call them free radicals. And contrary to what you hear in cosmetics advertisements, not all free radicals are bad.
That's the free piece of health advice from today, and this is a great place for me to say that this is the end of this free and radically interesting episode of Elemental. We'll be back in a few days as usual, but until then you can browse our expanding library of elements, either online at rnz.co.nz/chemistry or on your favourite podcast app.
And we're back next time with palladium. But until then, it's goodbye from me, Allan Blackman.
And me, Alison Balance. Mā te wā.